Alright, as mentioned before, lost signs can be used to find missing parts of triangles that are not right triangles. But as we're later going to see, it can actually be applied to right triangles. Theorem indicates that you have sine of the angle is over the side measure opposite to that angle is equivalent to sine of another angle opposite divided by the opposite side. And you notice in geometry you have angle A directly across it is going to be side A. Now we're going to look at why law of sines works. We have law of sines proof here. What they do is they go ahead and draw a height where it has to be perpendicular, and then they use right triangle trick. You notice that there's a right triangle, so there's two right triangles. First we're going to look at right triangle ACD, and we're going to come up with a relation. Now we sketch that right here just so that we see what we're looking at. Here's angle A, here's angle C. This is side B, now this is H, and this is D. So again, we're only looking at this triangle ACD right here. Now I'm going to go ahead and choose angle A, and using SOHCAHTOA, which is right triangle trig, based on the information that I have the H given and the B given. So now let's go ahead and come up with our relation here. This one is the opposite side. This one is the hypotenuse. I don't have anything on the adjacent, so I'm going to use sine. I'm going to say sine of angle A is equivalent to opposite H over B. And right now that's the only relation that I can come up with. I'm going to manipulate it or solve for one of the variables right now, but let's move on to another right triangle. Now let's go ahead and do right triangle BCD. So if you want to resketch it, you can do so. Here's angle D, or point D rather. This is C up here, B. Opposite this right triangle, I have A, then I have H. This time I'm going to choose angle B, and the same thing as before. I have information on the opposite, and this is the hypotenuse. So I'm going to use sine like I did on the other example. So sine of angle B is equal to opposite, which is H, over hypotenuse, which is A. Now I have two relations here from these two right triangles. And I notice that they both have H in common. I'm going to go ahead and solve for H on both of these. Multiply by B to cancel out this on this other equation. We'll multiply by A and multiply by A. That way these two divide out. And now I have that B times sine of A is equivalent to H. And on this one I have A times sine of B is equivalent to H. Now from these two equations, again, since they have the H in common, I'm going to set these two expressions equal to each other. That B times sine of A is equivalent to A times sine of B. Now with a little bit of algebraic manipulation, I'm going to go ahead and solve for one of the variables. Not necessarily solve for one of the variables, but simply try to come up with this theorem 8.8. You can see here that if I divide this by B, the only reason I want to do that is so that this divides out, but whatever I do to one side, I have to do to the other side. Now at this stage, I'm left with sine of A is equivalent to A times sine of B over B. Now here, again, we're not necessarily solving for a variable here. I'm just going to go ahead and have sine of B over B being multiplied by A. So I'm going to divide by A so that I can cancel it. And again, our goal is to look something like this. I can see here that I have sine of b over b. That's why I divided by a. But whatever I do to one side, I have to do to the other side. Now you can see here we have sine of a over a is equivalent to sine of b over b. Now in a similar way, you can choose a different angle. So let's say angle C. You can come up with this other portion right here, this sine of C over C. Like I mentioned, this is just a proof, or one proof, to show why law of sines has this relation.